All right, let's just jump right in. Think about it for a second. We live almost our entire lives inside this digital world, right? And it feels, well, it feels solid, permanent, totally unbreakable. We trust it with our money, our jobs, our friendships. But have you ever really stopped to think about what's holding it all up?
Yeah, that quote really just nails it, doesn't it? It gives you this sense of awe, but also there's a little bit of anxiety there, right? Because the real truth is the foundation of our entire tech world is way, way stranger and a whole lot more fragile than you'd ever guess.
And that's really the big question we're tackling today. What is this tower standing on? So let's take a look under the hood at the hidden architecture of our world. You're going to see it's a system held together by, well, trust, a whole lot of luck, and, you won't believe this, a few seriously overworked volunteers.
The source material for this actually calls it a liturgical lament for the tech stack, which is just a perfect way to put it. We're about to go on a tour of the pillars holding everything up, the, let's call them, load-bearing absurdities that somehow make our digital lives possible.
Okay, so before we even get into the code or the software, we've got to talk about the physical stuff, the body of the internet. You know, the cloud isn't actually up in the sky. It's very much down here on Earth, made of real metal and wires and glass. And it all starts with two things, the power grid and these giant cables lying at the bottom of the ocean. And this is where it starts to get a little scary. See those massive transformers that basically run our power grid? They're all custom built. If one of them goes down, there are no spares just sitting on a shelf. The lead time to get a new one is like 18 months, but the grid itself can only handle being down for seconds. Our entire civilization is basically running on a handful of these iron giants with literally zero backup.
And that's just the power. What about the data itself? This shows you the other huge physical vulnerability. Get this, 95% of all international data zips through just a few hundred fiber optic cables. And where are they? Just lying on the ocean floor. They get snagged by ship anchors, they get rattled by earthquakes, and, I'm not making this up, they occasionally get bitten by sharks who get confused by the electromagnetic fields. Seriously.
Okay, so that's the physical hardware. Now let's move up a layer to the invisible rules that tell all that data where to go. If the hardware is the body, then these protocols, they're kind of like the nervous system. And here's the wild part. A huge chunk of it basically runs on the honor system. A perfect example is something called BGP, the Border Gateway Protocol. Just think of it like the internet's global post office. It directs all the traffic. Now, you'd expect a system like that to have all sorts of security checks, right? Wrong. There's nothing. It's based entirely on trust. It's like a campfire circle where everyone just pinky swears they are who they say they are. So back in 2008, Pakistan accidentally told the world, hey, we're YouTube. And for 2 whole hours, the entire internet just believed it. Most of YouTube's traffic just vanished into a black hole. That's how fragile this thing is. And it's not just trust in these abstract systems. It's trust in actual specific people. Here's another one for you. For our digital world to even work, every single computer has to agree on the exact time, right down to the microsecond. It's crucial for everything, from stock trades to just making a secure connection. So where does that time come from? Well, one of the most critical time servers on the entire planet is maintained by one guy in a basement in Denmark as a passion project. The whole globe's sense of time is literally in the hands of a volunteer.
Which brings us to our final pillar, and honestly, maybe the most important and most fragile one of all, the people. We're talking about the often unpaid, almost always unrecognized folks who are the final line of defense for, well, everything.
This chart really says it all, doesn't it? It shows this insane imbalance in our digital world. On one side, you've got basically every Fortune 500 company on the planet, and on the other, the open source software they completely depend on, which is often maintained by just one person, in their spare time, for free. The whole global economy is literally being held up by the goodwill of unpaid strangers on the internet.
And sometimes, that one person is the only thing standing between us and total disaster. A perfect example just happened. A bad actor spent 2 years carefully building up trust in the open source community, just so they could sneak a major backdoor into a critical piece of software. And you know what caught it? It wasn't some fancy AI security system. Nope. It was one tired engineer who noticed a tiny 500 millisecond lag and just decided to care enough to figure out why. That's it. That's what saved us.
So you have to be asking, how? How on earth did we end up here? How did we build this incredible, essential, and frankly, terrifyingly fragile cathedral on what looks like a foundation of mud? The answer is actually pretty simple.
It was never designed to be this way. It just accreted. Accretion. It's just a fancy word for things gradually piling up, layer on top of layer. Our entire tech stack is basically built on the fossilized remains of old projects. Each layer started as some clever hack to solve a problem right then and there. Nobody ever intended for it to become planetary infrastructure, but, it worked well enough, so we just kept building on top of it.
And it all happened in a few key stages. First, we just built for the moment, not for the long haul. We came up with temporary solutions that were never, ever meant to last. But then, the internet just exploded. It grew so fast that by the time we looked back and realized those temporary hacks were now holding everything up, it was already too late to change them. We ended up outsourcing our trust individuals, and the whole thing just became so ridiculously complex that today, there isn't a single person on the planet who understands how it all works. Not one.
And just when you think this tower couldn't possibly get any taller or any shakier, along comes AI. And artificial intelligence isn't just another app on your phone. Oh no, it's a fundamental new layer being jammed into the stack, and it's acting like a massive amplifier for everything, both our power and our fragility. Look, before AI, the tech stack was complicated, for sure, but it was mostly deterministic. You put something in, you knew it would come out. But now, we're shoving this powerful new layer, the AI model, deep down inside everything. And this layer is a whole different beast. You can't see inside it, it's not deterministic, it's probabilistic, and maybe most importantly, it's controlled by just a tiny handful of companies big enough to build it.
So AI makes us dependent in these brand new, kind of terrifying ways. Think about it. We're not just outsourcing tasks anymore, like sorting a spreadsheet. We're outsourcing judgment. And as AI gets woven into everything, from the tools that write our code to the systems that protect us, it creates this crazy loop. We start needing AI to manage the complex systems that AI itself helped build. And all of this puts even more strain on that fragile physical stuff we talked about, the power grids, the data centers, all the things that were already stretched thin.
And that's the central paradox right there. AI is making us more powerful, more capable than we've ever been. The lights at the top of our tower are brighter than we could have ever imagined. But it's doing it by piling immense new weight onto a foundation that we already knew was shaky to begin with.
So look, after hearing all of this, all the fragility, all the single points of failure, it's really easy to feel a little bit panicked. But here's the real takeaway, the thing that should blow your mind. The crazy part isn't that the system is fragile. The crazy part is that it works at all. The fact that this teetering, patched-together, trust-based tower of insane complexity actually functions day in and day out, honestly, it's nothing short of a miracle.
And that leaves us with one last big question. We all live our lives inside this miracle. We depend on it for literally everything. But now, you've seen how it's built. You've seen the foundation. So the real question we have to ask ourselves is, how long can a miracle last?
I want you to do something for a second. Just look at whatever device you're using right now to listen to this.
Yeah, whether it's a smartphone in your hand,
Well,
a sleek laptop on your desk, or even the dashboard of your car.
right. Look at the glass, the brushed metal, the seamless interfaces. It feels incredibly solid, doesn't it?
It really does. It feels permanent, like a marvel of modern, precise engineering.
Well, today we are going to shatter that illusion entirely.
We really are. We're taking a conceptual hammer right to the glass.
Welcome to today's deep dive. I'm your host, and our mission today is to explore a piece of research, a really fascinating document titled Our Technosphere's House of Cards.docs.
And I'm your expert for today. And I have to say, this document completely flips the script on how we view our modern digital infrastructure. It doesn't frame the internet and the global economy as this, fortified castle.
Not at all. It frames it as a fragile 7-part liturgy, like a sort of modern psalm about a teetering, precarious tower of trust, duct tape, and volunteerism that is somehow keeping our civilization from going dark.
Exactly. We want to understand exactly what is holding up your digital life and how dropping artificial intelligence on top of it is making that tower both incredibly tall and, frankly, far more unstable.
Okay, let's unpack this. If I had to synthesize what this research is telling us, it's like you and I and everyone listening are living in the luxury penthouse of a massive global Jenga tower.
Oh, that's a perfect analogy.
Right. We are up there blissfully streaming 4K video, completely unaware that at the very bottom, half the wooden blocks are just missing.
That is the exact visual.
Yeah.
And if we connect this to the bigger picture, The overarching theme of this entire document is that we didn't plan this global infrastructure. We accreted it.
We accreted it, meaning we just kind of layered it over time.
Right, exactly. We essentially built a planetary cathedral, but it's resting on the fossilized remains of 40-year-old graduate school projects.
Wow.
It's a system built by layering new technologies over temporary fixes. And those fixes just became permanent because everyone was, too busy building the next layer to go back and fix the foundation.
Which means we need to start by looking at the absolute bottom of that Jenga tower, the physical reality, because I think we have this tendency to talk about the cloud like it's, I don't know, weather?
Right, like it's magic.
Yeah, like it's this weightless, ethereal magic floating above us. But the digital world is extremely heavy. The internet is made of metal and concrete and physical space.
It is entirely grounded in the physical world, and the physical world is messy. The research starts with these iron giants, extra high voltage, or EHV transformers.
EHV transformers.
Yeah. There is this haunting image in the source material of a transformer humming a funeral dirge in a fenced-off field in Nebraska. These aren't the little gray trash cans you see on telephone poles.
No.
These behemoths, they're the size of the house, weighing hundreds of tons, filled with specialized copper windings and thousands of gallons of insulating oil.
And the research notes there are only about 200 of these specific giants keeping the United States grid alive, like 200 pressure valves for our electricity.
Yes, they step the voltage up for long-distance travel and step it back down so it doesn't just instantly vaporize our cities.
And what really got me was the supply chain reality behind them. You can't just order one of these on Amazon Prime.
You really can't. There are literally no spares sitting on a shelf anywhere. The lead time to build and replace one of these custom behemoths is 18 months.
18 months.
18 months of sourcing specialized silicon steel, meticulously winding the copper, testing and navigating complex heavy-haul logistics just to get it to the site.
But the patience of the electrical grid is measured in milliseconds.
Exactly. The grid must constantly balance supply and demand perfectly, or the frequency drops and the whole system automatically shuts down to prevent physical destruction.
So we have a system that demands instantaneous millisecond perfection to keep our servers running, but relies on hardware that takes a year and a half to replace.
It's terrifying when you think about it.
It brings a whole new perspective to cybersecurity. I mean, we talk all day about military-grade encryption and zero-trust architectures, but what does any of that matter if a confused squirrel chews through a vital control wire and shorts out a substation?
It doesn't matter at all.
Right. A single rodent can force 3 states back into the 19th century, rendering all that advanced encryption entirely moot.
The physical layer is the ultimate vulnerability. And those vulnerabilities don't stop at the shoreline. To move data globally, we rely on the salt-crusted arteries of the internet.
The undersea cables.
Exactly. 400 glass threads laid in the muck of the abyssal plain on the ocean floor.
And these cables carry 95% of our international data. We're talking bank codes, international communications, high-frequency trades. It's all shooting through these tiny glass threads in the dark via pulses of light.
We effectively moved the central nervous system of our civilization to the seabed, and we completely forgot that the ocean has never been our friend.
Right, it's a harsh environment.
Incredibly harsh. These cables are constantly at risk. A commercial ship dragging an anchor across a shallow shelf can easily sever the connection between continents. Submarine landslides and earthquakes snap them. And yes, even sharks bite them.
Okay, wait. I read that in the source and initially thought it was a joke. Sharks bite the internet.
It sounds like a joke, but it's a mechanical reality of how the cables work. Because data is transmitted as light, the signal degrades over thousands of miles.
So they have to install physical repeater stations along the cable to boost the laser signal.
Precisely. And powering those repeaters requires running high-voltage electricity through the cable alongside the glass fiber.
And that electrical current generates an electromagnetic field in the salt water.
Right. And sharks have these specialized sensory organs called the ampullae of Lorenzini. They use them to detect the faint electrical fields given off by the muscle contractions of their prey.
Oh, wow. So they sense the current from the cables.
They sense the current, they think it's a struggling fish, and they attack the cable. So you have this incredibly advanced digital society, and its ability to communicate across oceans is vulnerable to a hungry apex predator reacting to the electrical hum of our memes.
That is wild. So the physical wires are at the mercy of dragging anchors, squirrels, and confused sharks.
Pretty much.
But let's say the cables survive all of that. The physical layer is intact. That brings us to the traffic flowing through those wires, the software routing our data.
The logical layer.
Right. You would assume that the backbone of global finance and national security is governed by an incredibly strict, mathematically perfect set of rules. But the source material details how the protocols directing the traffic is arguably even shakier than the physical cable.
Oh, absolutely. The document focuses heavily on BGP, the Border Gateway Protocol. This is basically the postal service of the internet.
It's the system that allows different independent networks like your home internet provider, a university network, and a major cloud host to talk to each other and figure out the fastest path to send data from point A to point B.
But the mechanism of how BGP works is astonishing. It operates purely on the honor system.
The honor system.
Yeah.
Like a global GPS system where any driver on the road can just paint a new highway sign and every other car's GPS instantly, blindly updates to follow it.
Yeah, there is no foundational cryptographic authentication baked into BGP. It is entirely built on implicit trust.
Wait, you're telling me the internet doesn't have a bouncer? There's no ID check at the door of global data routing?
None. When a network router announces to its neighbors, hey, I have the fastest route to these IP addresses, the neighboring routers generally just believe it. They update their own internal maps and pass the message along. There's no built-in mechanism to demand proof.
Which explains the mechanics behind that notorious 2008 incident the research highlights. The government of Pakistan wanted to block access to YouTube, but only within their own country.
Right. So their national telecom sent out a BGP route announcement to its local routers. They essentially painted a fake highway sign that said, I am YouTube. Send all YouTube traffic to me, with the intention of just dropping that traffic into a digital black hole locally.
But the fake highway sign didn't stay local. The Pakistani telecom accidentally leaked that BGP announcement to their upstream internet providers.
And because BGP operates on the honor system, those upstream providers believed the announcement. They updated their global maps, and then they told their neighbors.
Within minutes, routers all over the planet were convinced that the absolute fastest path to YouTube servers was through a telecom in Pakistan.
The global internet just consumed the lie. Traffic from all over the world meant for YouTube was violently hijacked and shoved through Pakistan's infrastructure, which obviously immediately collapsed under the weight of it, causing a massive global outage for the platform.
We are literally a single configuration typo, a fat finger mistake by an engineer late at night, away from accidentally routing a European bank's secure traffic through a random server rack in a completely different country.
And it's not just routing that relies on these bizarre trust-based mechanisms. It's time itself. The research brings up the timekeeper's basement and NTP, the network time protocol.
Time synchronization is the absolute bedrock of digital security. It isn't just about making sure the clock on your phone is right. If servers don't agree on exactly what time now is down to the millisecond, the entire internet breaks.
Exactly. Think about cryptographic certificates, the mathematical handshakes that put the S in HTTPS and keep your web browser secure. They have strict expiration dates and timestamps.
Right. If a computer's clock is off by a few seconds, it might look at a valid security certificate, decide it's expired, and just refuse to connect to your bank.
Furthermore, data is broken down into millions of tiny packets when it travels across the internet. When those packets arrive at their destination, they have to be reassembled in the correct order.
And without precise, synchronized timestamps, that reassembly becomes chaotic.
High-frequency stock trades, which rely on microsecond precision to determine who bought what first, would completely collapse into disputes.
And the mechanism keeping this all synchronized is wild. The research introduces a man named Paul Henning-Kamp. He is sitting in a room in Denmark, running an NTP daemon, a background software process, telling the world what now is.
One man, maintaining a vital piece of the global clock, mostly just to see if anyone is still paying attention.
Which begs the question, why is it like this? Why is the logical infrastructure of a globalized trillion-dollar digital economy running like a small town's volunteer fire department?
And the answer goes back to that concept we talked about, accretion. The internet wasn't designed for a global public.
Right.
When BGP and NTP were written in the 1980s, they were designed to route packets between a few university mainframes or to sync the clocks on a handful of academic research machines.
The people connecting to the network all personally knew each other. It was an environment of high trust.
They were clever hacks to solve local problems. But then the network expanded so fast, commercialized so aggressively, that these temporary academic trust experiments became load-bearing global infrastructure before we had the chance to govern them or secure them.
You cannot easily rebuild the foundation of a skyscraper while billions of people are actively living inside it.
Exactly. Which
Yep.
brings us to an even more precarious layer. We have physical wires, vulnerable to the environment, and logical protocols that operate on blind trust. But the software running on top of those protocols relies on a different kind of vulnerability.
We outsource the maintenance of this infrastructure to exhausted, unpaid people.
The human vulnerability. The document calls this the load-bearing 11 lines. It unpacks the reality of open-source software.
Because most people assume massive tech conglomerates write all their own code from scratch, but they don't. It is vastly more efficient for them to build their commercial products using free, open-source building blocks.
Open source is the unpaid backbone of modern capitalism. According to the data, over 90% of Fortune 500 companies rely heavily on open source libraries to keep their lights on.
And many of these critical libraries are maintained by single, unpaid volunteers in their spare time.
The document paints this vivid picture of a stressed maintainer in a stained t-shirt who works a day job and then spends their weekends fixing bugs in a tiny piece of code that half the internet relies on.
And this maintainer hasn't had a pull request, which is when a developer submits a proposed code change for review, actually looked at and approved by another human being since 2017. They are operating in total isolation.
It means the global economy is deeply dependent on the goodwill, the free time, and the exhaustion thresholds of individuals. They could just decide to burn out, walk away, or lose interest tomorrow.
Here's where it gets really interesting, because malicious actors understand this human vulnerability perfectly. They know exactly how tired and isolated these volunteers are, and they are using it against them through supply chain attacks.
The research highlights the 2024 Exit Utils incident, which is just a masterclass in exploiting human fatigue.
It really is. A supply chain attack doesn't involve breaking down the front door of a server. It involves compromising the factory that makes the locks, so every new lock shipped out naturally comes with a secret master key.
In this case, the target was SSH, or Secure Shell, which is the foundational protocol administrators use to securely log into and manage servers remotely over the internet.
The attacker didn't just try to smash a firewall, they played the long game. They spent 2 entire years volunteering on a critical open-source data compression project called Exutils, which happens to be bundled into the operating systems that run SSH.
For 2 years, this attacker was helpful. They submitted good code, they gained trust, they took the load off the original highly stressed maintainer.
And once they had the keys to the project, they slowly and methodically carved a highly obfuscated backdoor ghost into the code.
They engineered it so that when an administrator tried to log into a server via SSH, the malicious code would secretly intercept the authentication process. If the attacker used the right cryptographic key, the backdoor would grant them silent, total control of the server, bypassing all passwords.
They were weeks away from this backdoor being distributed to millions of critical servers worldwide.
And the mechanism that stopped it wasn't a billion-dollar corporate cybersecurity suite. It was one tired engineer at a tech company who was doing some routine testing.
He noticed that logging into a system via SSH was taking about 500 milliseconds longer than it should, half a second of lag.
That lag was the tiny CPU cost of the hidden malicious code executing in the background.
And against all corporate instinct to just ignore a half-second delay and go home for the weekend, he actually cared enough to painstakingly reverse engineer the code and find the backdoor.
We built a machine that coordinates billions of people and trillions of dollars, but its final failsafe in that instance was just human attention.
The multi-trillion-dollar suspension bridge of our global economy was held up by a single, curious volunteer crossing guard. By all laws of probability, this system shouldn't hold together, yet, miraculously, it mostly does.
So we have this teetering, impossible tower made of 18-month transformers, blind trust BGP routing, and exhausted human volunteers. And now we are taking the most computationally heavy, power-hungry, and opaque technology in human history, and we are dropping it right on top of the tower.
Artificial intelligence.
We are entering the era of the AI multiplier, and it is deepening our structural dependence in ways we haven't fully grasped yet. The research frames AI as a new invisible layer wedged between the network and the user.
What exactly does that mean functionally? Why is it different from normal software?
Previously, computing was deterministic. You had hardware, an operating system, and a program. If you look at the code, you could trace exactly why an input resulted in a specific output. If X happens, do Y.
Right, it's a predictable path.
But AI specifically, the massive neural networks we are deploying now, is probabilistic. It is a black box of billions of weighted mathematical connections. This creates a new kind of fragility called epistemic dependence.
Epistemic meaning relating to knowledge. We are relying on a load-bearing layer of technology that produces answers, writes code, and manages systems, but no single human being, not even the engineers who built the model, can fully audit or mathematically trace exactly how it arrived at its output.
We are functionally guessing at its inner workings.
And the danger is that we aren't just using AI to automate math or sort spreadsheets anymore. We are outsourcing cognitive primitives to it.
We are asking models to classify data, prioritize network traffic, detect security threats, and make recommendations. We are outsourcing human judgment.
When you do that, you are implicitly depending on the worldviews, the biases, and the blind spots embedded in the massive opaque data sets used to train those models. Let me push back on that for a second, though, because the pitch for AI is that it is supposed to be the ultimate problem solver. Shouldn't AI be the thing that fixes this whole precarious mess? Couldn't we just deploy an AI agent to scan all those open source libraries, find the 500 millisecond lag, and perfectly secure the BGP routing tables so the honor system isn't an issue anymore?
That is the great paradox of the AI era. Yes, AI is a powerful prosthetic. It is an incredible multiplier for human capability, and it absolutely can find bugs and optimize code faster than a human. But the counter-reality is that AI accelerates complexity far faster than it accelerates human comprehension.
It builds things we can't fully understand, and it also physically weighs us down even more. We are right back to the heavy physical reality from the beginning of our deep dive.
We really are. AI requires a staggering amount of infrastructure. It demands hyperscale data centers. It requires advanced GPUs that are back-ordered for years.
Training these models requires petabytes of data shooting through those same undersea cables that the sharks like to chew on, and it demands enormous, continuous amounts of electricity flowing through those 18-month lead time transformers.
Because of the sheer capital and energy required, AI heavily centralizes power into the hands of a few massive entities.
It is recursive complexity. We now have AI models writing code, other AI models configuring the cloud infrastructure to run that code, and yet more AI models monitoring the cybersecurity defenses to protect that code.
We literally have black boxes defending black boxes. We are building the tower so tall and automating the construction so fast that nobody can even see the foundation anymore.
It is a technosphere that is too complex to audit, too fast to follow, and too interdependent to isolate.
Which brings us to the view from the apex. This research brings it all directly back to you, the listener.
You are standing at the very top of this impossibly fragile tower. You sit down at your desk. You run a command like npm install to download a nested web of dependencies for your software project, or you type armfrf as an administrator, and you are balancing your entire digital operation on a single thread.
The whole structure shivers beneath you. Corporate marketing departments love to brand this precarious layering as digital transformation.
But looking at the vulnerable transformers, the blind trust routing protocols, the exhausted volunteers, and the black box AI models, the universe just calls it a miracle it hasn't fallen yet.
It really is a miracle.
So what does this all mean?
It means we have to hold two contradictory truths in our minds at once. We are more structurally dependent than we have ever been in human history, teetering over a deeper abyss of complexity. And yet simultaneously, we are more technologically capable than ever before.
We can communicate instantly, cure diseases, and coordinate globally. It is terrifying, and it is a marvel.
But if we connect this to the bigger picture, it leaves us with a profound question about the future. If we are currently building our digital world on the fossilized remains of academic projects from 40 years ago, temporary hacks that just became permanent laws of the internet,
Right?
what happens 40 years from now? Will future civilizations be forced to build their societies on top of the fossilized remains of today's incomprehensible black box AI models?
Wow. Treating them not as software code that can be easily updated, but as mysterious laws of nature that simply cannot be questioned or understood.
Exactly. It's something to think about next time you pick up your phone.